Being in CERN, doing the research, talking to some of the physicists was very interesting. We spent some time with the reduced crew. That was fun and exciting. They liked the book. And they were very helpful creatively.
The idea of CERN was a very powerful dream when it was built. You can imagine Europe coming out from the Second World War, which was devastating for the world, but it was even more devastating in Europe because not all the countries in Europe were on the same side. CERN from '54 up to now has essentially grown, stabilized, become the most important laboratory in the world for particle physics. We are trying just to push the limit of the knowledge of nature beyond what we know now.
Now, did you want that in English or in a language?
In English.
Okay.
Everybody speaks English in CERN.
Okay.
I found that it was kind of false, unless two people of the same country just were chit-chatting.
Right.
Then, otherwise, everybody speaks English.
Okay.
For centuries, science has been trying to understand on a literal basis so many aspects of our world, including the moment of creation.
Take your places, people.
Atlas and CMS.
Currently at CERN, particle physicists are conducting experiments hoping to recreate the Big Bang. They're hoping to understand how our universe came into being.
We are really working at the very frontiers of human knowledge about the universe. That concept is something that really can capture the imagination.
This is highfalutin stuff that, again, Dan Brown was somehow ahead of the game, and our timing is kind of perfect as far as making this movie goes.
One of the great things about working at CERN is that you're working side by side with people from over 100 nationalities. Today you will find some very unexpected working relationships. You'll find Indians and Pakistanis working on the same project. You'll find Arabs working with Israelis. We have 2 Saudi Arabian students working on projects here. So you just find that when people are all engaged in the same project with the same curiosity about the universe, then anything else is secondary. People can really work together, and that's a wonderful thing about CERN. Our convention says 2 things that I think are extremely important. One is we must not do any research of military nature at all, and the other says that we must publish and make as widely available the results of everything that we do. CERN has an open door policy. We're open to the public 6 days a week. We have open days every few years where we invite people in, and the last time we did that, the estimate was something like 70,000 people came here over a weekend. CERN is evolving into a global lab. We have 20 European member states today. But in the current project, the Large Hadron Collider, there are something of the order of 40 collaboration agreements we have with other countries. There are a number of countries that have what we call observer status at CERN, which means they come and they take part in the CERN Council's meetings. They don't vote, but they take part in the discussions. And those countries have made quite substantial contributions to the project. CERN has a staff of 2,500 people, and their job is to build the basic infrastructure that allows the research to be done. So CERN builds and operates particle accelerators. That's what we're here to do. Everything is made of particles that interact in various ways, and what we're studying is what the composition is, how they interact. And that's what a particle accelerator does. It smashes them together and watches them interacting with each other.
It's a way of studying the origins of the universe, to try to isolate what some people call the God particle.
The Large Hadron Collider is a technological marvel, really. It's the largest superconducting installation ever built.
The LHC is about 27 kilometers in circumference, so this is a circular accelerator. It's about 100 meters underground, nice, it's quite safely tucked away. There's a tunnel which is about 4 meters in diameter, in which the accelerator sits.
So it'll operate at minus 271 degrees. That's 1.9 above the absolute coldest temperature you can ever have, and colder than outer space. The vacuum inside it is such that there's 10 times more atmosphere on the moon.
These are kind of big 7-story high detectors which aim to capture every single aspect of this collision. Each of the sub-detectors is looking at a different aspect, measuring the energy, where it took place, picking up all the particles that came out of it. And then what they do is, of course, try and reconstruct what actually happened at the collision point.
The LHC is a big time machine. It brings us to a 1/10 of a billionth of a second after the Big Bang. So there we can understand how the universe is made. This, for instance, might have an incredible outcome. With all our understanding of the world, of the universe, we understand only 4% of what is out there. Because the other 96% is made by what we call dark matter. Matter which doesn't emit light, for instance. One of the things we might find here, the famous God particle, the Higgs, because on all the things we have understood, we don't have understood yet what is the origin of the mass. And this particle is an explanation.
It's what gives all matter mass, the thing without which we could not exist.
You're talking about the moment of creation.
Imagine if we could discover that there are other hidden dimensions which are maybe very compacted, because now we are living in a cold universe, 13.5 billion years after it was built. The big change of paradigm of the beginning of the last century was just to understand that it's not three-dimensional and time is a separate, but they are all together.
We're about to start the machine this year. It's a focus for particle physics around the world. It's going to bring us some amazing new discoveries about the universe, and we expect it'll have an operational lifetime of 15, maybe 20 years.
That canister contains an extremely combustible substance called antimatter. We need to locate it immediately.
The origin of antimatter is really interesting. Matter is made out of small particles which form nuclei, and then a nucleus with an electron, that's an atom. Now when you create these particles from energy, you always create them in pairs. You always create an electron, for example, and its antimatter twin, the positron. It's like, imagine you sitting on the sand, a stretch of sand, and you dig a little hole into the sand. Then you put the pile to the side. You cannot create the hole without making this pile of sand at the same time. And that is basically somehow the best way to think about antimatter. It's a kind of a mirror image of matter. We think that this transformation of energy into mass happened during the Big Bang. Immediately the problem came up saying, well, if that happened during the Big Bang, you would have 50% matter and 50% antimatter. So our universe should be made 50% out of antimatter. But we have lots of evidence by looking out into space with radio telescopes and listening to all kinds of signals that there is no antimatter in the universe. So where did it disappear? And there is still a program here at CERN which looks into this question, because it's one of the biggest mysteries of the universe. What happened to the primordial antimatter?
I'm quite familiar with incendiaries, Ms. Vetra. I've never heard of antimatter being used as such.
Well, it's never been generated in significant quantities before.
How do we create antimatter? The way to do it is to transform energy into mass. We accelerate particles to very high speeds, speed of light almost, and then we let it collide with a target. And when these particles hit the nuclei, the energy is transformed into new kinds of matter and antimatter, 50-50. Once you have made antimatter, you have to be very, very careful not to bring it in contact with ordinary matter, because as soon as the two meet, they will destroy each other. They will go into pure energy. So what do? We pump out the air out of our whole apparatus. Strong magnetic and electric field keep the antiparticles on their track, so they are circulating without touching any matter in this ring. And then we let them go into experiments which can trap the antiprotons and suspend them in so-called penning traps.
In an airtight nanocomposite shell with electromagnets on each end. But if it were to fall out of suspension and come in contact with matter, say the bottom of the canister...
If you take 1 gram of antimatter and 1 gram of matter, you would produce something which corresponds to about the energy released in 3 Hiroshima bombs. That is a lot, but we cannot produce 1 gram of antimatter, so there is no risk that we ever produce such a bomb. If you take all the antimatter which has been produced here at CERN over 10 years or so, and you just calculate what energy they could release, that's about 10 billionth of a gram, that would just light a light bulb for about 3 minutes. So it's not very much. Why do we study antimatter? First of all, we just wonder if antimatter is just exactly the same as matter, if it's a perfect mirror image, or if you look at the mirror very precisely, if there's a little scratch in the mirror. And that is the key question, and it's related to the question if at the beginning of the universe it was absolutely 50-50, and then something happened and the matter survived over the antimatter, our type of matter was left. If the symmetry would have been perfect, we would not sit here. So antimatter, in some sense, carries the mystery of our existence, and that's why we are interested. Antimatter has a few existing or maybe possible future applications. One application of antimatter is that we can look inside of us. It's used for what's called a PET scan. PET stands for positron emission tomography, and you can make pictures of your brain without going inside. So antimatter has helped a lot in order to understand the functionality of the brain, and it can also locate tumors in your body. For therapy, we are currently thinking maybe one could use antiprotons, also antimatter beams, which are directly into your body in order to destroy tumors which cannot be treated any other way.
There are in Europe and in the States and in Japan a number of centers which use protons, which are much less devastating for the side tissues because their release of energy is totally different from the release of energy of gamma rays, photons that they are using in the normal radiotherapy. And with these, you can cure tumors without surgery. Or you can get to tumors where surgery cannot get because it is making collateral damage which is too big. So we are promoting technologies in a sense that then they The mission of CERN for mankind is just to push the frontier of knowledge a bit further. This can be only achieved if is a global challenge. It comes to benefit not of few, but of everybody. The other important thing is that while we are pushing this frontier forward, we are also, in my opinion, the best language for peace.
Go back to work. Change the world.
There's a constant stream of evolutionary moments in mankind, and for a great portion of the world, when a new pope is made, that's the beginning of a brand new era. Everything else was before and this is after. And when that Large Collider does its job, humankind is going to be in the same sort of position. This was before mankind was able to create this, and now it will be after mankind will be able to create this.